Okay, so I'm not exactly sure where the camera quit out on the last segment there, but we were talking about this hydrogen bonding effect, and it's a very significant phenomenon that causes the properties to deviate of a substance from what might otherwise be predicted. These two molecules, again, water and hydrogen sulfide, because of their shapes, should demonstrate really similar properties. But this amplified dipole moment that exists on these OH bonds really causes water molecules to tightly attach or adhere to one another. And so pulling those apart from each other then, which is what the boiling point is really all about, is a lot harder. Thus the boiling point is extremely exaggerated for water versus where it would be without the effect of hydrogen bonding. It's a good 100 to 200 degrees higher. Water would be boiled well below 0 degrees Celsius were it not for hydrogen bonding. There's a trend that we can look at, an image in your textbook figure that shows that. And the density is much more enhanced as well. And this is part of the reason why ice, solid water, floats in liquid water. Most other solid materials, their solid is the more dense phase compared to the liquid. I erased the pictures that I had up here earlier, but in the liquid phase our molecules usually pull apart from each other a little bit. They have that more degree of freedom of motion. But in water, the hydrogen bonding really snaps the molecules tightly together. To form the solid phase, the molecules have to arrange. They have to come up with a pattern, a regular repeating pattern. Perhaps you've seen close-up images of a snowflake or an ice crystal, right? So the molecules have to move out to make that pattern that introduces more space between them. Thus the density is decreased because you have the same mass but now in a larger volume. That's going to be a lower, less dense subphase. That's why ice floats on top of water. Very different world, right? If ice didn't float actually, if lakes and ponds and things froze from the bottom up, right? It'd be very different if it weren't for this hydrogen bonding phenomenon. Okay, all right, we're ready to do some examples now so that we can assign the intermolecular force of attraction. All right, left my pen off camera here. I'll be right back. There we go. So let's identify. I like to ask the question in this manner. Identify the strongest intermolecular force present. All right, and I'll tell you why I asked the question that way in just a second. All right. So if we were considering molecule that I put up earlier, SF4. For SF4, the logic process that we need to go to assign the strongest intermolecular force present here, first we would need that Lewis dot structure that we drew up earlier. So real quick, we can throw up a Lewis dot structure. We see this lone pair of electrons, so we would say this is a polar molecule. Because it's a polar molecule, we know it's got a slightly positive and a slightly negative side to it. And that's what's going to allow one SF4 to attract to another. So we would say that dipole-dipole attractions exist, and they're the strongest of the forces. Okay? Up here in this right-hand corner of the board, I'll list now from strongest down to weakest. Ionic, ion dipole, H bond, hydrogen bonding, dipole-dipole, dipole-induced dipole, and then dispersion. Okay? So dipole-dipole is right about the middle. The reality of this molecule, SF4, is that it actually also possesses dispersion forces, all right? We could think of these as like a ladder, especially when we write them in this direction, right? And that every substance has, as a minimum, dispersion forces, and then you would work your way up the ladder. Well, SF4 cannot have dipole-induced dipole because it's not a mixture, right? The SF4 molecules all have dipoles, so we kind of cross that out in this case, and then we can go up to dipole-dipole, and it's not capable of hydrogen bonding, so that's all the further up this ladder that we would go. All right. The book in Mastering Chemistry asks you to list all of the intermolecular forces present. So you have to list out several. So for SF4, you would say dispersion and dipole-dipole. Again, I like to simplify it and just say, tell me how far up that ladder, what's the strongest intermolecular force that you're going to see demonstrated in a substance. Okay? All right. How about carbon dioxide, CO2? A quick Lewis dot structure for this molecule. Okay. 2 double bonds from the carbon to the 2 oxygens, all right? Don't worry about the lone pairs on the oxygens. Lone pairs are on the central atom that we're worrying about. This molecule is symmetric, right? So there are dipoles pointing to each oxygen. This is just like AX2, which we saw a long time ago in this video, but that's where we started. So because it's symmetric, it's nonpolar. So what's going to try to hold one of these to another one of these would be the dispersion force. That's all that we can have in this case, dispersion forces. Okay. How about sulfur dioxide? Looks like it's going to be the same as carbon dioxide, SO2 to CO2, but we have to, this is why we have to be careful about our Lewis dot structures. Sulfur has 2 more electrons on it than carbon, and it's going to cause this to be a bent structure, actually. Again, I'm seeing it flat, and you can draw your bonds at whatever angles you want, but you have to remember, in reality, this molecule is going to have these 2 oxygens slightly pointed down. They're going to come out to one side. So you're looking at my hands representing the 2 oxygens right now, and then if I turn around, now you're looking at the sulfur. So you are clearly going to have a polar molecule here because you're seeing different sides because of that lone pair of electrons. So this is going to have dipole-dipole intermolecular forces. Sodium bromide, NaBr. All right, NaBr. Hopefully, if you start polishing up your skills again, shouldn't take you any time at all to realize, wait a minute, that's an ionic compound because it's got a metal in it. Right? Remember the periodic table has the line on it, a red stepwise line starting right around aluminum in the upper right side that steps down to the bottom right hand corner that divides all the periodic table on the left side as metals and then the smaller group of nonmetals on the right of that line. Anytime you cross that line and grab something from each side of it, you've got an ionic compound as far as we're concerned, all right? So if it's ionic compound, ionic intermolecular force of attraction would be present, okay? Let's look at methanol, CH3OH, all right? I don't need to look any further in the case of methanol than the OH that's present right there. When we write a structure's formula this way, as opposed to CH4O, we're being given a big gift. This is telling us that we have O directly attached to H. If we were given this formula, the version here, we would have to maybe figure that out. But right away we see O attached to H. We know it's superpolar. Actually, we go even further and we know that this is going to exhibit hydrogen bonding. Okay. All right. Let's look at a couple cases of mixtures and see how they come into play. What if we tried to mix fluorine, F2, and how about SO2? I chose SO2 because we already know that it's polar, right? Well, F2, hopefully it won't take you long. This is like we started earlier, X to X, right? The two fluorine atoms are going to have the same electronegativity. Therefore, it's going to be a non-polar bond. And this is a non-polar molecule. So the attraction that exists between a polar and a non-polar substance will be the dipole-induced dipole. Okay, dipole-induced dipole attraction. Right? It's not going to be the greatest of mixtures here. And we have this adage, this old adage that likes dissolve likes very well. Things of similar intermolecular force dissolve in one another very well because they all have the same ability to grab hold of one another. Either they all have their hands out in the case of polar molecules, or they all don't have their hands out in the case of non-polar molecules. All right? So that's where that adage comes from. All right? How about let's continue with this SO2 and CH3OH. Now SO2, again, we assigned polar earlier. CH3OH we said had hydrogen bonding. But in the case of SO2, let me draw it this way. Oops, sorry. I'm going to draw the oxygens pointing towards sort of the methanol group. Okay? It's tempting to say that we could have what we're looking for because hydrogen bonding in reality, and I did not draw this accurately earlier for you, that's when the video expired. Hydrogen bond is really the H of one attached or drawn to the O or nitrogen of another. So this dotted line right here is the H bond. And that's why you need to be able to both donate and receive. We can see that, yeah, this H could be attracted to this O right here, all right? But there's no H's on SO2 to reciprocate to the oxygen on methanol. So it's sort of, we need to be able to give and receive in order to call the attraction hydrogen bonding. So in this case, while methanol to itself would be hydrogen bonding, we want to remember that hydrogen bonding is just an extreme form of this molecule being polar. So it sort of defaults back to the more generic polar molecule, and we've got polar-polar, so this mixture would be held together by the dipole-dipole intermolecular attraction. Okay. The same thing would be true if we tried to take our sodium bromide, our NaBr, and put it into water. Sodium bromide was ionic, we had earlier. Water can exhibit H bonds, but there are no hydrogens or oxygens over here on sodium bromide to participate in hydrogen bonding to the water. All right? So we can't have hydrogen bonding across these two different species, and we'll treat water in this case as being polar. So this is the ion-dipole attraction that we have listed up here. So that's the strongest attraction that we can get in this circumstance. All right? So that's a nice list of examples for you to consider. In Blackboard for the course, you should find a worksheet that has many more of these intermolecular forces of attraction for you to consider. I'm going to wrap up this video on intermolecular forces. I can see it's been going on for quite a while. Thanks for your patience and your participation in watching this outside of class time. There's going to be another video available where I go into the topic of vaporization of liquids and what's called vapor pressure. And you'll need to watch that one before our next class lecture as well. So thanks a lot. Take a little break and then come on back for the next video.